Welcome, everyone. Today, we're doing an architectural teardown of OpenGo. We're going to explore a massive challenge in robotics. How do we give a robotic dog real-time skill switching and embodied intelligence without it completely losing control? Our core theme today is simple. To unlock true potential, we actually have to constrain the brain. Let's start with the big problem, the danger of physical hallucination. On the left, we have what we call the semantic illusion. In a simulation, a large language model can generate a brilliant, perfect-looking plan, like telling a robot to leap exactly 5 meters over rubble. But on the right is the physical reality. On actual hardware, an unconstrained LLM often ignores the physical embodiment of the robot. It ignores scene geometry and exceeds actuator limits, turning a linguistically perfect command into a catastrophic physical failure. So, how do we fix this? By structuring the LLM's action space. Look at the difference between standard end-to-end LLM policies and our OpenGo skill library. Instead of letting the AI spit out unpredictable raw motor commands, OpenGo uses bounded, predefined skill parameter pairs. Instead of black box generation, we use explicit, self-checking code modules. And most importantly, instead of behavior degrading sharply in novel environments, our functions remain completely immutable and highly modular, with hard-coded constraints blocking any invalid moves. Here's what that looks like in practice. OpenGo bridges the gap between semantic reasoning and physical execution by integrating a high-level LLM with the OpenClaw control framework. At the top layer, a human user simply types a task description into a communication platform, like Feishu. In the middle translation layer, our dispatcher receives this and selects the right skills while monitoring memory and state. Down at the hardware layer, the robot handles perception and relies on an internal, emergency stop safety tool to make sure nothing goes wrong. Let's zoom in on what we mean by a bounded skill. Think of each skill as a locked cube. The actual execution logic, the core function, remains totally locked and fixed. However, the LLM is allowed to adjust the hyperparameters, tweaking variables like distance or speed to adapt to the specific task. Surrounding all of this is a cage of safety bounds that enforce strict preconditions, meaning the skill won't even execute if the terrain or limits are wrong. And we don't just trust these skills out of the box. We enforce safety before deployment. New capabilities are never, ever deployed directly to the hardware. First, they undergo a strict code review to verify interface compatibility. Then, they move to simulation validation to test robustness. Only after passing both stages are they integrated into the skill library and admitted for the LLM to use. When it's time to act, our dispatcher acts as a semantic funnel. It takes the task description, human instruction, and the perceived scenario, and funnels them into the large language model. The LLM operates exclusively over predefined skills. Its only job is to select the correct sequence based on the scene, and assign hyperparameters strictly within those valid templates we talked about. The output is a safe, validated sequence of skills and parameters. But the system doesn't just stop learning. It uses continuous refinement through execution feedback. Every time the robot executes a task, it logs task signals and error logs. If a skill works great on a specific terrain, the system increases its priority. If it fails, the system automatically adjusts the default execution durations or turning radii. It refines parameter bounds without ever having to rewrite the underlying control code. What does this mean for the user? It means we can bring human intent directly to the quadruped. You don't need manual policy engineering anymore. Inexperienced users can just type, move forward and then turn around. The dispatcher catches this natural language guidance, applies the high-level control skills, and routes the OpenClaw execution state, plus any error logs, right back to the user in the chat. The results are seamless transitions across execution states. We validated this on the Unitree Go 2 platform. Because of this architecture, the robot can transition in real time between standard locomotion like moving forward or turning around, all the way to complex posture adjustments and trick control like backflips and dancing. Now, it's not totally perfect. Let's talk about the cold start system tax. The first time you invoke a skill, there is a massive delay, an initialization overhead caused by LLM parsing, retrieval, and parameter instantiation. As you can see on the chart, latency scales directly with the number of input parameters the LLM has to validate. Moving forward, the solution here requires caching mechanisms and skill preloading. We also hit some bottlenecks when scaling complexity. If you look at multitask response times, you'll notice a significant nonlinear spike. Total response time does not scale linearly with the skill count because the system absorbs a heavy tax from inter-skill scheduling, state transitions, and resolving dependencies. Coordinating multi-skill execution is currently our main bottleneck for smooth, long-horizon tasks. So, to be transparent about the current boundaries of the architecture, we are fighting two things. First, LLM response latency prevents ultra-rapid, time-sensitive decision-making in highly dynamic environments. Second, delays in skill invocation create fragmented, staggered physical motion rather than perfectly fluid navigation. To quote the blueprint directly, the structural trade-off for high-level safety is temporal friction at the execution layer. To wrap things up, OpenGo proves that direct motor control is the completely wrong objective for large language models. By anchoring LLM reasoning inside a validated, parameter-bounded skill layer, we get to keep the semantic flexibility of AI while guaranteeing physical safety. The resulting paradigm is clear: constrain the action space to unlock reliable embodied intelligence. Thank you for watching.